Hi, everyone. My name is Caroline Griffin. I'm Riot's Director of Operations, and I'm super excited to have Chris Lehenbauer with Phase Doc with us today at the Riot Lunch and Learn series. The Riot Lunch and Learn series is the place where we spotlight all of Riot's partners. And we are super excited to have Chris to talk about what's your duct tape to electronics ratio today. Just a couple of quick reminders before I hand it over to Chris. This session is being recorded and will be posted to Riot's YouTube channel and the meetup page where you registered for this event. Chris has graciously agreed to share his presentation materials, so that will also be shared out after the presentation. If you do have any questions, feel free to use the chat box, but Chris has also agreed to allow those who are interested to unmute yourselves at the end of the presentation to give it more of an interactive feel, to kind of replicate those in-person lunch and learns that we're missing so much. But without further ado, I will hand it over to Chris. Chris, thank you for being with us today.
Thank you so much for that kind introduction, Caroline. And thank you to Riot for inviting us to speak today. We've enjoyed being part of the Riot community. It just keeps getting better and better. I am Chris Lehenbauer. I am the CTO and co-founder of PhaseDoc Inc. We're a small manufacturing company here south of Raleigh, North Carolina. And while we do have a product line, and we'll be mentioning that today, this isn't really about us and our product line. It is about things that we have learned along the way to this point. We thought we would share those things and hopefully be able to kind of accelerate some folks who are in the product development process as well. So thanks again. Hello to everyone, and let's dive in. So today we are going to talk about the physical aspects of prototyping, and in particular about the mechanical components. We ourselves don't do electronics. We are mechanically oriented, and so we focus on the packaging and the mounting and the transportation of your project. Most of the people that we work with already are well versed in electronics, so we're on the other side of that. We'll touch a little bit on what we think are the important stages of product development, and in particular, where we think you can leverage your own efforts to accelerate that process most effectively. We will be talking about some of the resources that are available to you commercially to mechanically put together and present your projects. But a big part of the presentation is also about what happens when you can't find what you need and need to go out on your own and develop what you need with your own resources. So just a brief touch on our product development philosophy. I think most people now are comfortable with the notion of failure, and really we think that product development comes down to accelerating the failure process so that you can get the badness out of the way and get to the good part of what you're trying to develop. Of course, what we're trying to figure out is, do you have the right technical configuration, and do you have the right market demographic, and have you nailed that down? And the way to really get to that point is to figure out what your assumptions are, get them out into the real world and test them against the people who will be buying your product or interacting with the product. We think that one of the best ways to accelerate that process early on is to do as much of it as possible yourself in the early stages. So we'll be talking a fair amount about what you can do and knowing where your limits are when to pass the baton. But before you pass that baton to specialists whom you will enlist in the process, have you answered all the questions that you need to answer before you do that? So really it comes down to, do you have the right it? And that's actually the name of a book that I read a couple of years back that really formulated a lot of my thinking on the prototyping and development process. I would recommend it highly, and we have put that into our resources document that Caroline will disseminate after the presentation. Savoya writes about this. Really, the underlying point of the book is, are you building the right thing? Not are you packaging it, or marketing correctly, and manufacturing, but have you started at the right fundamental point? Do people really want what you are proposing to give them? So that's the idea behind the right it. And a big part of what he says is you need not to use other people's data. You need to develop your own data, right? And again, the way to do that is to get out of your head and in front of the real world. One of the really interesting concepts that Savoya puts out is a prototype instead of a prototype. Of course, everybody knows what a prototype is. A prototype, I don't want to say that it is it's vaporware, but it has some. So here's a story that may illustrate that quickly. Uh, Decades ago, IBM was deciding whether to invest in a speech-to-text computer. In other words, should they develop a computer that would understand the spoken language so that people wouldn't have to type? Of course, now we have that, but this was, literally decades ago. So before they did the first thing, they did an interesting experiment, and they put a speech-to-text computer in a room, and they had people interact with it. Now, in reality, what was happening was there was a computer, there was a microphone, and there was a monitor. But nothing was happening in the computer. There was the microphone just went into another room. There was a very fast typist in the other room. And as people spoke into the mic, of course, their words appeared on the monitor in the other room. And so they could gauge the interaction of the human with the speech text without developing any actual hardware or software. Interestingly, what they found was they thought, oh, we're going to sell a bajillion of these things. And they found that actually, when they watched people interact with this computer, they didn't like it enough to pay what it would have cost. So they shelved that entire product, but they shelved it before they spent the first development dollar. So that's the notion of a prototype versus a prototype. That's really failing early before you start to invest money in something that may not be appropriate. And the key there is essentially fast and cheap, right? So we want to iterate quickly and for low dollars before we start to invest in something that may suck up a lot of resources and not come back. So there's the concept, and that's kind of our whole philosophy as we approach our prototyping. So our background then, as we go into this, I am not an industrial designer. I'm a manufacturing engineer. And so I know that when I get to a certain point, I have to make that handoff. So I'm not advocating, I'm not speaking as an industrial designer, and we also don't do really high volume production. What we do is we help you at the early stage of your prototyping and perhaps in very low volume production. And we come at that as a company based on an extensive background I have in a broad range of materials and processes, both for prototyping and in high volume production. So I approach things essentially as a manufacturing engineer, and I know where my limits are, and we'll speak to that, knowing where yours are, but also leveraging your strengths, which may mean that you have more capabilities than you gave yourself credit for. Having said that, when you reach a point where you say, well, I've done what I need to do, and I need to go to an industrial design firm to take this to the next step, or even beyond that, to a product development firm that can take us into full production, you should certainly do that. These are firms that are local. They're part of the Riot ecosystem. These are folks that we have talked with before and worked with before. Highly talented, highly recommended. So again, these will the folks both at Loud Design and Touchstone for industrial design, and then the DNA Group and Porticos for going beyond and taking you to high volume. We'll put those out in our documents. Do feel free to reach out to them. Our point is this: when you come to them, they will likely ask you a whole host of questions. It is far better for you to have those answers rather than have to go back and get them or pay a lot of money to have them get those answers if you were able to do that. How can we accelerate and simplify that handoff right there so that it's optimal. That's what we like to talk about. So when you prototype or start developing, typically before you get to production, I see roughly 3 stages. Everyone pretty much nowadays starts with a CAD, a computer aided design model, right? And as you well should, because the CAD world is so sophisticated now that you can not only get very close to what that looks like, I mean, photorealistic rendering, but you can simulate almost any physical property you can think of in software. And so you should be doing that. And we'll talk a little bit about what some options are for you to do that. However, there are always things that a digital model cannot tell you. And that means that you should start interacting with even a very, very simple physical model sooner rather than later in parallel with your digital model, because that physical model will show you things that you did not expect to see and that the computer may or may not tell you. So that low fidelity physical model, I think, is a very first step. And I believe it's one that should be taken earlier rather than later. And it shouldn't cost much and it shouldn't take much time, but it should be early. And it should evolve in parallel with your digital model. Now, after that low fidelity and the digital model have kind of settled down and stabilized, then it's time to build a high fidelity prototype, which is well beyond what Savoya would call your prototype, right? So now your high fidelity prototype is definitely going to start showing you some aesthetics, some form, as well as function. And at this point, if you're developing a consumer-facing product, I strongly recommend that this is a good point at which you bring in an industrial design house, because I know my own limitations and I can only make things so attractive. And like it or not, aesthetics matters tremendously in a consumer-facing product. You will be judged on your appearance as much as your performance. So we have these 3 stages. Today, we're really going to focus on that center point, right? So I'm going to assume that you are comfortable with the CAD world and the computer-aided design step here. You can get your digital model, but how do we get from there to at least the low fidelity physical model and maybe a little bit past towards the high fidelity? So that's kind of the focus of today's discussion. To start with, I mentioned at the beginning, I'm a big advocate of using what's on the shelf, right? Especially early on. So here are just some simple things that you can do to mechanically tie your components together, as certainly as you're ideating or early conceptualization. This is called a Sunfounder RAB, and essentially it's a piece of plastic that lets you mount the most ubiquitous boards out there, Arduino and Raspberry, if you're using those just to conceptualize things. I know, of course, people have moved far past that. In fact, one of the things I would ask you to do as we go through this process today, what is helpful to us is if you would put into the chat or at the end of the discussion today, tell us the types of boards and the direction you're going in with the hardware that you use on the electronics side. That would be very helpful. But to this point here, this is a very simple way to package up basic boards and a breadboard. You can carry it around and it's cheap, 10 bucks on Amazon, off you go. It's not a bad way. A step up from that is the Stego board, and this is geared more, this is showing a Raspberry Pi, but is geared, it'll actually take small motherboards. It's geared more towards classic computer components, you know, hard drives, 2.5-inch drives and things like that. It's got a whole pattern in there, and there's much more complicated than what you're seeing here. That's also a good way to help you accelerate using some off-the-shelf options there. This is an open source option here. It's called the Open Makers Cube. It's out on GitHub. You build it yourself, and essentially you adapt it to what you want to do. You can build pretty much anything you want on there. No, it's not pretty, but it's highly functional. And at this point, that is really the objective here. So there's something else you can do and customize to your heart's content. So I will put what we do out there as well. This is a quick look at our product. The concept here is these are the basic components of it. This is a project built out on our platform. We like to describe it as Legos for electronics. We have adapters that you mount your electronics to. They then snap into this grid of holes so that you can place your components and then wire them up. It's very sturdy. You then can put a cover on it, put it in a backpack, drive it around, whatever you want to do, show it to your clients, and then iterate as you go. These are some of the things that some of our own customers have done. On the left, you see is a very large wall mount. I think that was like 20 Beagle boards in a firmware test setup for a large company in Raleigh. And then some of the things that our other customers have done to kind of customize what they can mount, just to give you an idea of the density and the flexibility of this approach. This is something I really like. So on the left there, you can see a NEMA rated case from Bud Industries, which I'll come back to in a little bit. Those are great, but how do you put your stuff into it and get it in and out easily so that you can work on it? We've adapted our system to that, and we'll speak a little bit more to that later on, but also hanging things on the wall. So we're shooting for flexibility and adaptability. To that point, and you may have seen this on the Maker's Cube there, DIN rail. If you are not familiar with DIN rail, that is the aluminum extrusion that you see there at the front. It is sitting on our product, but that's the point there is that DIN rail is its own standard. And there are components that you can then just snap on, a whole array of components that are adapted to DIN rail. You can also buy small nylon adapters that you can put on your own components, snap them onto DIN rail. So that's a really handy way to organize and mount a lot of electronic boards in very high density fashion. So I'm a big proponent of DIN rail, and that's why we incorporated that into our own ecosystem there. So some of the considerations as you're developing this, thinking about your mechanical approach to things, how easy is it to do and how quickly can you iterate? Obviously, you want to iterate as much as possible. Is it secure? People almost always want to transport things, and will your mounting take some shock and vibration if that's what you needed to do, if you're putting it out into some kind of a harsh environment? Can you move it around either on a vehicle mount or something that moves, or just carry it around yourself? And of course, how many different things can you put in there? And then, of course, there are a lot of engineering aspects to it. How are you going to dump heat out of this thing, right? So if it's enclosed, how are you going to extract heat from it? How do you get power into it? Signals, there's a question. Do you want to shield it? Do you want to get signals out? So do you want to attenuate or not? That certainly impacts the choice of materials you make. Plastics are good for getting signals out, metals not so much. So those are all considerations that you want to think about as you choose your components. As you've gotten past the early kind of low fidelity iteration thing, your design has stabilized, and now maybe you have started to condense it smaller. You're using smaller components, maybe some custom components. There are some simple things like these Solar Botics acrylic cases. They come in different sizes, and they are they're versatile. You can modify them by either drilling or lasering them to mount things on there, and they're cheap and accessible, and they look pretty good. So that's a really good way to kind of take it to the next step as you need to start to show your product to other people to get feedback. A lot of people, of course, are familiar with Pelican cases. They come in a wider range of sizes, and there are other manufacturers as well. Mounting your components in there, it takes a little bit of work, but you start with a very stable kind of platform if you do that. And then coming back to the NEMA enclosures, two of our favorite sources for those are Bud Industries and Polycase. The Polycase, I think, is over there on the left with a clear top, and the center and the right show, again, the Bud Industries. They come in a wide range of sizes and materials. And the one thing I would point out there is if you're going to put things outside, you want to realize that there are some cases where the materials are rated for UV and outside exposure. And there are other things to consider too, like impact resistance. So polycarbonate is much more impact resistant, but more expensive than acrylic. So just be aware that your material selection may have a bearing on where you're going to put whatever you do. So there, kind of summarize this whole thing. I essentially want to say, go out and look. We'll put out some of these resources there, but there's a lot more available than most people know. Please use something that already exists. If you can start, that will definitely save you time. But of course, you may need to go beyond that. A lot of times you'll have to modify these things. You want to get cabling in and out. So there are glands that you can drill a hole in the side of a NEMA case, put the gland in there, feed your cable through, and that will give you some water and ingress protection as well. So there's a range of things there. Please avail yourself of it. What happens when you can't find what you need? Well, that's when we go past and start talking about how do you design and build your own enclosure or mechanical components. And what I want to do here is I want to talk about three different buckets of tactics that kind of define three different approaches, kind of from the most accessible, if you want to say the easiest, to the more challenging and least accessible. I think one of the things that everyone is by now is familiar with is 3D printing. I think it's very accessible. It's relatively straightforward. If you can build a 3D model of what you want, getting a sample of your 3D model is pretty easy once you figure that out. So we'll start there. Something that not a lot of people know, and I didn't know, and I've been manufacturing for 35 years, until we got our own laser cutter and engraver. Boy, that is a really, really versatile, very fast tool for prototyping in a number of ways. So I'm a big fan of that. It's a little bit more hands-on than 3D printing, but I would say at least as versatile and as useful, and you can get faster results in a larger envelope. And then a lot of people are familiar with CNC routing. Everybody's pretty much heard those, the term, and it is, I've done CNC since the late 80s. I'm a big fan of it. It is challenging, both in terms of getting the code to the machine so that you can actually run the machine, but also the work holding and understanding the material removal processes. It's definitely not something where you just walk up to a machine, throw in some G code and start and push the button and walk away. So I definitely don't want to discourage people from that, but I do want to say there's kind of this progression from easy to more challenging, and I would put CNC on the more challenging aspect of that. So at this point, you may say, well, that's all well and good. All of those things take some kind of machinery that I don't have or some software that I don't have. How do you propose that we use them? Well, there are options available to you, perhaps more than you realize. There are at least two, I don't want to call them maker spaces because they aren't really. They are labs, they are manufacturing labs that are available to the professional community for product development. One of them is actually Riot itself, which has the Riot Lab downtown in the Raleigh founded building. And it's quite well equipped. Certainly it is predominantly geared towards electronics fabrication, but they have three key components that address each one of the things we talked about. They have a 3D printer, they have a small laser, a Zing laser, and then they have a Shapeoko desktop CNC router. So we'll talk a little bit on the other side of this about how to engage Riot Labs, but that is certainly a good starting point for you if you want to be exposed and use these types of tools to get started there. Hangar 6 is a facility out in the Research Triangle Park, west of Raleigh. It's a very advanced lab, whereas Riot Labs is, there is not a fee per se to use Riot Labs. You need to be part of the community, and you need to talk to the Riot folks to make sure that you're ready to use that, and that they know that you're using that, and that you can do so safely. Hangar 6 is it is a commercially oriented manufacturing lab specifically focused at product development. So it is not a makerspace as you would conventionally think about it. You don't go there to make breadboards for Valentine's Day. This is instead a very, very well equipped manufacturing lab. There is a monthly subscription to use the facility, but they have everything from multiple 3D printers, including some very large ones. They have 2 lasers. One is actually an entry-level industrial laser. And then they have not only a router, but an actual vertical machining center, so advanced CNC equipment. So that is available to you as well. It is at cost, but they have someone on site who can train you up on a lot of those things. And so if you are in a serious product development process, that can save you a tremendous amount of money and time by availing yourself of Hangar 6. There are also 2 more maker-oriented spaces in the Raleigh area. I'm exposed to Riot Labs and Hangar 6. I've not been to Shop Space or the Maker Space. I have just looked at their websites. They are there. They do not have as much advanced CNC, but they have Makerspace in particular is very woodworking oriented. Shop Space has a number of different technologies that they put out there, so that's worth checking out. Those are also at cost, but if they fit what you're developing, I would put those out there as resources. So before you say, hey, you're telling us about things that we can't really use because we don't have all those fancy machines, they are out there and available to you. So check those out if this makes sense to you. So let's spend a few minutes talking about these 3 different approaches to prototyping, starting again with 3D printing. Now, a lot of people have been exposed to it, and so you may think you understand the whole process. Once we start, in full disclosure, we use 3D printing not only for prototyping, but as a bridge to injection molding. So we actually print production parts day in and day out for sale commercially. So we've learned a lot the hard way about how that's done. And the key with 3D printing is, of course, you need a 3D model in CAD that you can send to the printer. And if you don't have that, well, that's a sticking point. Most people, of course, most of the engineers that I see who are not working in a large company typically will start off using Fusion 360. It is an Autodesk product. It is a very capable product. I will say that I find it has some limitations if your design gets very complex. If you have a somewhat less complex design, it works perfectly well. And I've seen people build out very complex designs on Fusion 360. So please don't think that you can't do that. It is certainly capable. SolidWorks typically has been used commercially. I really see no limitation to SolidWorks in terms of the technically what you can achieve. Of course, the problem with SolidWorks has always been the cost. Fusion 360 is free. All right, as the last time I looked at the rules, it's free to individual makers and to startups with annual revenue of less than $100,000 a year. I believe that's the most recent rules. SolidWorks typically did not have a free version. They have just recently, to my understanding, introduced a very low-cost version. I think it's $99. Now, having said that, I do not believe that version is licensed for commercial use.
I believe that is it's a learning platform, and there is a learning curve. So if you're learning SolidWorks, that's the way to do that. However, SolidWorks does have an entrepreneurial license, and you apply for it. You have to be a startup, and I think there's some revenue limits. So you have to be pretty early stage. But it's a pretty simple application. We actually did that at PhaseDoc early on. If you pass the application, they will let you use a very I think it's a pretty advanced version of SolidWorks for a year, free of charge. There may have been a nominal charge, but I don't think they actually billed us for that. So you essentially can use SolidWorks commercially for a year. Of course, the clock starts ticking at that point, and after a year, you then need to go to a paid subscription. But there is actually an on-ramp into the paid tiers. So if you work with your local distributor, there is a way to kind of ramp up into the full version. So I would encourage you, essentially, when you're looking at choosing between these two platforms, if you see a long-term reliance on CAD software for your company, I would encourage you to think about the move to SolidWorks earlier rather than later, instead of starting on Fusion and then shifting later. There are other Autodesk products that are at higher price points. You can go into Fusion and go over to those in the Autodesk stack as well. So I'm not discouraging that. But just think about your long-term end goals as you make your choices, and because that is a very fundamental choice early on in the process. So that was a big digression into software, but it is the foundation for all three of these approaches. So I thought it was worth a bit of a digression. There are also open source CAD packages out there. I mentioned OpenSCAD. It's a different approach than either Fusion or SolidWorks. It's essentially a mathematically based parametric package in which you kind of describe your geometry mathematically. It sounds bad, but it actually works pretty well for certain cases. So I would put that out there as an option for you. Essentially to say, choose your software carefully and wisely, because there's a fair amount of learning curve to get to it. Once you're up on that curve, you don't want to make the switch. So think about downrange as you make that decision. So once you've designed whatever you're designing in your software for 3D printing to work, you have to export your model in a format that your slicer for your 3D printer will understand. And that is almost universally an STL file, right? So whatever CAD package you pick, make sure that it has a conversion to STL so that you can then send it to your slicer. And that is kind of the workflow with a 3D printer, is you design it in CAD, convert it to STL, feed the STL to the slicer. And the slicer is essentially a very, very smart, very fancy CNC programming package that understands what your 3D printer wants. So it will ingest your STL file, it will slice it literally, and for each of those slices, it will develop what's called G-code. And the G-code is what your 3D printer understands. It's what makes your 3D printer move around and print your part. So that is kind of the workflow there. Main point being, and certainly this is true, Fusion, SolidWorks, OpenSCAD, almost all 3D CAD packages will export to STL. So that's typically not an issue. Just make sure that whatever you choose does do that. So you've sent your file to the printer, you've sliced it, and it's running. Think about whether 3D printing is appropriate for you. Basically, how big is the part? Typically, 3D printers aren't large, although Hanger 6 has a very large printer. So that may not be an issue there, but certainly check out your particular printer and see if what you're doing fits there. Material is a big point. I'm going to come back to that. And also dimensional tolerances, right? I've been astonished. So we have a couple of Prusa Mark III S's that we run. We have three of them actually. And I have been amazed at how consistent and accurate they are. We've printed thousands and thousands of parts and they are very consistent. So I would speak highly, and that's not a very expensive printer. That's $750 if you assemble it. So that's pretty astonishing to me. Another point I would say, as you design your parts for 3D printing, it's easy to design a very complicated part that cannot be 3D printed. So once you start printing more and more, you will understand what the 3D printer likes and what it doesn't. A lot of times what I'll do is I'll break a complex part down into subcomponents and I will glue those together. Depending on the material you use, super glue works typically really well on most of those materials. So that's just something to think about. As you start designing, think about how that printer, what it wants to see, and design your parts to that. A little bit of a design for manufacture exercise right there. And if you have to glue them together, it's a lot better than post-processing and taking out supports and rafts and that sort of thing. You can, if you find something that works for you, certainly, of course, there are a lot of resources out there. And a lot of times I will use those things because they don't fit what we need exactly. I'll just use them as a jumping off point for designs. So definitely do scour those resources out there. There's a lot of good stuff out there. Boy, materials, this is probably the biggest thing right here. Everybody, I think, starts out printing PLA. It's the most beautiful material you can find. It prints easily, looks great, it's awesome until the sun hits it. And then you're going to be very sad. It does not deal well with even ambient heat. It will warp, and once it warps, there's nothing you can do. It's not going back. So we'll prototype in PLA because it's beautiful and it's fast and it prints very reliably. We do not do any production parts in PLA. We had a bad experience with that early on. We use ABS for everything. ABS it's much stronger than PLA, and the biggest thing is it is much more heat resistant. So we've really never had a problem with that. And we've had parts, and our parts are stressed pretty hard out in the field for 2 years now. And really they don't break. I'm astonished by that. The challenge is that ABS is much more difficult to print with reliably. So you're gonna have more of a learning curve there. But, and basically you use more heat. If you can, use an enclosure. PETG, I don't have any experience with it. I think it acts a lot like ABS, and I think that's what Prusa makes their parts out of. So there's another option for you. I mentioned that for you. Some options for you. You know, printers are not that expensive. You're going to do a lot. Go ahead and pop for one. Word of advice: I would not start at the $250 entry level printer. I've never seen that work out well. We've had really good luck with the Prusas, and of course, and those are like $750. You can go, you know, under $2,000 will buy you a lot of very good printer. $250, not so much. However, if you don't have one, I would strongly suggest there are a lot of good service bureaus. You email them your STL file. They'll estimate it online. You email them your STL file. A couple of days later, either you can go pick it up, there are a bunch locally, or they'll mail it to you. That is a great way to go. And then, of course, they are available locally. Hangar 6 has them, or Riot Labs has them. That's the most used tool they have in their shop. So there are some options for you there. So there was a fast, high run through on the 3D printing thing. Let's talk a little bit about laser engraving. And the key to laser engraving is on the software side is both simpler and more difficult than 3D design, believe it or not. Everything you do in a laser is going to be two-dimensional because that's all it can do. That's the nature of the game. However, so that seems like it would be simpler, and it is certainly on the design end in Fusion or SolidWorks. However, the challenge is that you don't program a laser the way you do a CNC machine. And I say that with a caveat. There are two classes of lasers. There are industrial lasers, which are driven by G-code. And then there are the cutting and graving lasers. That is what we have. They're smaller, not necessarily small, and they do not appear to your software like a CNC machine. They appear to your software like a printer. And in fact, whereas a CNC machine is driven by G-code, most of the lasers, the Trotec I have, the Epilog Zing that is at Riot Labs, they use HPGL, right? So it's Hewlett Packard's graphic language. So that is a printer driver, and you need to use something like CorelDRAW or the Adobe equivalent to ingest your file from your software and convert it to something that your laser will be able to process. So there's that extra step. And in order to do anything extensive with the laser, you're going to have to learn a little bit about CorelDRAW. So there is that extra step. Once you get past that, it becomes a very fast, very, very versatile approach to making parts. Typically, what you will do is you will extract a vector file, and the best, most reliable format for that for lasers is DXF. That's an ancient Autodesk file format, neutral format. Everybody knows about it or has heard about it. So you dump your 2D file into DXF, and you send the DXF into CorelDRAW. In Corel, then you will program the laser. And that is a little bit obviously beyond the scope of what we're talking about today. But once you nail that process down, becomes a very fast way to get parts made. Laser cutting is so much faster than 3D printing. So that's one advantage. And if you have a large laser, which is, they're definitely around. The Zing at Riot Labs, I think, is like a 12 by 18. We have a 32 by 20, and then Hangar 6 has even larger ones than that. I think they're as much as 48 by 48. So you can get larger output much faster. And the other thing you can do with the laser is you can engrave. So it can act both as a cutter and as an engraving tool. And that can make your products look really good, putting your logos on or instructions or things like that. So it's very, very versatile. The biggest thing, and I would probably drive to this, is choose your materials carefully for the laser. I said that there are two classes of laser, industrial and then the engraving, basically the engraving lasers, which will also do some cutting. Yes, there are, but there are also different types of lasers in those classes. So there are CO2 lasers, there are fiber lasers, and those different lasers cut different things. Most of the lasers that you're going to run into that are available to you are CO2 lasers, and they typically will do well with organic materials. So they will cut wood. They will do a fabulous job on acrylic sheets. So they love plexiglass, masonite. A CO2 laser will not cut sheet metal. It will engrave some types of sheet metal. So there, with that caveat. But choosing your materials is key. Fiber lasers, on the other hand, are a different animal. They can engrave things, typically metals. They love metals. And with enough wattage, a fiber laser can definitely cut some metal. So that is a consideration there. I will say this, before you put, so plastics typically go well into a CO2 laser. A word of caution, you cannot assume that all plastics are compatible with a CO2 laser. Some not only will not cut, they may catch on fire, and they may create some very noxious fumes. They can create nerve gas. So there is a difference, a vast difference between acrylic sheet, plexiglass, and Lexan, which is polycarbonate. CO2 lasers love acrylic. We cut so much acrylic. That's the basis of our product. It will not cut polycarbonate. Do not put Lexan in there. So those are, certainly there are different engineering properties to those two materials. There are certainly times when you want to use polycarbonate because it's so much more impact resistant, and that is certainly true. But you can't use a laser to process that. You have to mechanically cut that. So you need to use a CNC router. Don't put polycarbonate into a CO2 laser. If you have a question, that's one of the most important things to ask about. If you're not familiar with the laser, do some online research and make sure to talk about any questions you have with an authority on site if you have any question about that material choice. Okay, so if you stay within bounds, it's a fabulous tool. It's easy to get out of bounds and get into trouble with that. So there's the caveat there. And also, I will say this: there is a fire risk with the laser. So we don't look at our laser as a set and forget. We don't walk away from the laser. Someone actually is there all the time. We have a CO2 fire extinguisher next to it, so you need to be cognizant of that. Typically, if you pull the air out of the laser with a fan, pretty high vacuum fan, you'll be fine. But do realize that there is a chance for fire there. So with those caveats, fabulous tool, but there are some of those. Again, there are a lot of service bureaus out for lasers. Lasers are more expensive inherently than 3D printers. So you can buy a relatively large Asian printer for a laser for about $5,000. A higher end American or European laser on the scale what we're talking about is 10, 20, or 30,000, depending on the size and the wattage. And there are some small entry level lasers for a couple thousand that are really good. But be aware that there is definitely a cost hurdle there. But you have a lot of options locally. Again, service bureaus and the maker spaces before you get to the point of buying that. I wouldn't advocate buying one unless you're really going to drive it a lot. So then kind of wrap up here. The CNC router, I don't want to discourage people from that. You would use the same software to design that. CNC can be either 2-axis or 3-axis, right? And people really, when we say 2-axis, they'll hear the term 2.5-axis, 2.5D. What does that mean? That means that you cannot move all 3 axes at the same time. So what happens is you position the Z-axis, which is your cutter, at the height you want to cut, and then you might make simultaneous X and Y moves. That's 2.5D. If you can simultaneously move X, Y, and Z to make something sculptured like a mold for a tennis shoe, that's full 3-axis. Most people will start with 2.5D. That is certainly what I would suggest. The point with routers, with anything CNC, is you have to develop G code. Now remember, when we talked about 3D printers run on G code. The beauty of that is they develop that G code entirely by themselves in the slicer. Not so much with any CNC tools like a router or a milling machine. You need to generate that G code, yes, using software, but that is a non-trivial step that you need to learn. And typically you got 2 choices. You can either get software that lives inside your CAD package, or you can export your CAD model, like we did the CorelDRAW, into what's called a CAM package, computer aided manufacturing. Import the 3D model there and program it there. There's a lot to that, and I don't want to minimize that. However, there are things that you can do with this technology that you can't do any other way. If that is true, it's worth learning. And you can do a tremendous amount with a relatively inexpensive desktop router, like the Shapeoko at Riot Labs. You can get a good one of those for $2,000 and do a tremendous amount. I will say this: the key to happiness in CNC is not really the metal removal. It is the work holding, because the cutting forces involved are much, much higher than they are for 3D printing or for lasering. I mean, in laser, all you do is you lay the material on the table and you push the button, because there are no cutting forces. That is not true in CNC. So work holding is the key, and that's really, cutting is easy, work holding is hard. Make sure that you are holding your workpiece securely before you push that button and run your G code. So I don't want to discourage people from CNC. I do want to say there are more challenges there, and that's kind of the progression you want to go to. If you want to do that, Hangar 6 is great because they have a very experienced person there in the shop who can guide you through that process. I would suggest taking advantage of that. Or you can, of course, you can always outsource things. And I would definitely encourage that. if it's complex. One last thing I want to touch on before I close out this section: choose your materials. I have started, there are more materials out there available to you. We machine a lot of things out of sheet plastic, especially HDPE. That is an incredibly good material. So materials choice can really open up what you can do with your CNC. These are just some of the things that you can use, but the materials range is much broader for CNC than it is in any other way. And of course, again, different ways to get into it. Definitely, if you buy your own, if you buy a vertical machining center, well, you got to be serious, because entry level, it's about $50,000. And you really got to be making a lot of parts to go that route. So I'm not encouraging that. There are a lot of ways to get to that point before you reach that. So again, some of the resources that we have: Riot Labs and Hangar 6 in particular, and then Shop Space and Maker Space as well. I was just going to touch very quickly on a couple of tools that I would recommend every engineer have, even if you're an electronics type. I think cordless screwdrivers are great for putting stuff together. This is not a big one. This is a small one. It's like a, I don't know, 5 volt or something. I have a 7.4 volt DeWalt. Boy, these things are great, and they don't cost a lot. Weak point is probably the bits. Get yourself some high quality bits, but these things are great. This one here, hey, everybody needs some electronic calipers. They're terrific because they will let you measure things very accurately, either in metric or in English units. 4 different ways. You get inside, outside, step in 2 different manners there. And they have become really, really inexpensive. You can get pretty good ones there on Amazon. So I get a couple of those, one in the shop, one on the desk. Don't leave home without it. And in fact, that's what this one is. This is the 2.5. Yes, it's another set of calipers. These are plastic, and the advantage is when you drop them, they don't break. So these go into the cargo pants when you head out to do procurement, because you're not going to break those. Astonishingly, they're not any cheaper than the really nice electronic ones for a high-res plastic calipers, but they're worth it because you have it on hand, and it's the way to go. Last but not least, here are some resources for materials. Amazon, of course, has a lot of materials. Bolt Depot for hardware, excellent, fast resource, a lot of stuff. E Street Plastics for sheet acrylic. So if you want plexiglass in a wide array of colors and thicknesses in small pieces, shipped out reliably to you, E Street Plastics is the way to go. If you need big sheets of plastic, Piedmont Plastics here in Raleigh is good. And they also have other things besides acrylic. We buy our HDPE from them. And but that is not you don't walk in and say, hey, I need a 1 foot square piece of 1/8 inch acrylic. That's not how it works. So you're going to need to buy a 4x8 sheet. It's for commercial purposes. But once you get beyond small quantities, that's the way to go. And then we mentioned some of the other sources for products off the shelf. Hey, if you all are interested in some of the things we do, my partner and marketing manager thought about putting out a discount code. So that's going to be out there. Come to our website, check us out, see what we do if you think we can be helpful to you. So there it is. I have managed to say every word in English at a very high rate of speed. And I would love to open this up now to questions. Just unmute your mics and fire away if you want to show us what you've got. By all means, do that. Caroline, did we have any questions, or is there anything I missed that I should do?
Thanks, Chris. We did have one question in the chat from Julio. What would Chris say? What would Chris say is a level of complexity when it's a good idea to migrate away from Fusion 360?
You know, here's one thing I've noticed, Julio, and this surprised me. So I thought it would be a highly complex 3D model. Actually, when you see, when we showed you that product before, we've got an array of holes. That as soon as that array gets very large, they're using an algorithm to process the geometry that really bogs it down. And so I've been a little astonished. Sometimes you can put enough just simple 2D geometry, the quantity of simple 2D geometry is high enough that it will bog down the processor. And so I would have said, oh, if you're building a really complex solid model with lots of moving parts in an assembly, but sometimes it's actually been when you get enough volume of simple 2D geometry. And so that may bite you as well as a lot of complexity on the 3D. But I've seen people build some really complex 3D assemblies in Fusion. What I find, Julio, is that the processor slows down and it taxes my patience. And SolidWorks is just much faster. So I don't want my software slowing me down. It'll do it eventually.
Mm-hmm.
I don't want it slowing down the design process. Does that make sense?
Yeah. Is there anything like on like open source or just like freeware side that you recommend? Or if you just hate Windows and you don't want to
Man, I have
join the
lived
dark
with
side?
that so long, for years, and I haven't really found it. Now I will say this as well. So I'm not saying SolidWorks is the be all end all, but they do have, for instance, if you want to learn and play, they have a military veterans license. So you can, if you are a military veteran, you can use a SolidWorks license to learn. Again, it's not supposed to be used for commercial purposes, but at least you can get your feet wet there. But I don't have a good recommendation on open source. I wish I did. I have this fantasy of creating the ultimate open source CAD package because I spend so much time there. Boy, that's a tall order, my friend.
Gotcha.
Yeah.
Yeah.
Yep. Sure
Okay.
is. Thank you. That's a good question. When I wrestle with myself, it's like, good.
Chris, those were the only questions I saw. And yes, thank you, Barbara, for putting that discount code RIOT, RIOT21, if you go to phasedoc.com.
Yes, and what we're going to do is we're going to put the slide deck out, I think, in PDF form, but we also have a Word doc that will convert to PDF that has all the resources that we mentioned. So, and we'll put the discount code in there. Yes, I would ask, so I'll push a question out to you all to kind of help us figure out as we kind of fine tune our own product line. What kind of boards are you all using and what kind of components are you all using in the projects that you do? I sense people are migrating certainly towards the smaller, more powerful boards as things do get smaller, more powerful. But what are you, the community, using as you prototype and develop your products? Just open question.
I mean, I can say what I've been using because I kind of have to go in a little bit.
Sure.
So after the very first prototyping in those perforated boards, you can put wires. I try to move like as much stuff as I could and as fast as I could to just surface mounts.
Right.
Just get the PCB done in like PCB Way or that other one, PCB JP or something in China. It's kind of quick and you just put it on a hot plate or something with your components and you can do it that way. And I've been using I have at home one of those really entry level SLA printers.
Yeah.
And using the hard resin, the one that's kind of the mechanical toughness one, it served me well. It's very tough actually. So it's been good, and precision it's enough for what I do, and I'm trying to build it kind of like a compact device. But I think to get me further from what I have, what I'm aiming for my next prototype is just have not only them do my PCB, but just assemble it with their pick and place and have some sort of service, either SLA or filament print at least the main conduit for my part, and then we have a glow forge. I can make the case myself, maybe for
Yeah.
initial run. That's
Glow
at least
forge
that's
is
been the plan.
excellent choice. That process you described makes perfect sense. Is starting, and that's typically what we see people doing with our stuff, is you start with discrete components on a breadboard and everything wired together, and as soon as you get that stable, boom, go to PCB and ship it to Asia. Yeah. Yep.
Yeah, my fear is that the part that ends up 3D printed, which is a kind of like a gas bath that is kind of it's branching, and it has like 2 windows for light, and a flow sensor, but I don't have much of an idea about injection molding. What I know is that you make 2 shells and you have to put the melt plastic. So I think, what if this is completely untranslatable to like injection molding? Like, sorry, you got to start all over again. Like this.
That is very
or it's
good
very
consideration.
difficult mold to make, expensive.
Yep. And honestly, I would say, and you're asking the right question at the right time, don't design yourself into a corner, because injection molding is its own entire, boy, you could talk 3 days about that. And you're right. How you can 3D print things that cannot be injection molded, and vice versa. So you're right to be concerned about that. And the best thing to do is, where are you physically?
Rally.
Oh, good. There are design to part shows. I should have mentioned this. So design to the digit 2 part, design to part.
Yeah.
They travel, and what they do is they bring in contract manufacturers, and we're at time, so I'm gonna wrap this up. Sorry, Caroline. The design to part is bring your component, and they'll have 200 people there, and they'll have 50 injection molders, and you can talk to all of them, and they will tell you you can or you can't. Definitely, that's a good step. So look them up. They got them in different areas. The next one in Raleigh is going to be in November. I don't know if you can wait that long, but they got them in different areas of the country. So think about that. Thank you. That was great.
That's great to know. Thanks for the advice.
Absolutely. Caroline, good. Hey, we're over time. Thank you.
You're totally fine. And I'm happy to leave the Zoom open if anybody wants to stay on and chat with Chris. I don't know if that even fits your schedule, Chris, but thank you so much. I know we had a smaller crowd today, but I always say quality over quantity. We had a great group, and very wonderful presentation, Chris.
Thank you. That's very kind.
For all the questions and the discussion, y'all. Again, you can find this recording on Wright's YouTube channel and the meetup page where you registered, and Chris has said he will provide the presentation in those resource documents. So we'll get those out to you shortly, y'all. I hope everyone has a great day. Take care.
Thank you so much.
Bye-bye.
Thanks, everyone.
Thanks. Bye-bye.
Bye now.